Hello everyone, my name is Tim. I'm from the University of Bern and today I'll be discussing our work on label-free estimation of clinically relevant performance metrics under distribution shifts. The motivation behind this work stems from the urgency of monitoring a model's performance after deployment. Due to changes in the underlying distributions between training and deployment datasets, model performance can degrade and potentially harm patients if not addressed. On the validation set with labels, we can compute any performance metric we want, but in deployment, labels are usually not available, so we can't easily track the performance. Recent research has addressed this by estimating accuracy from model confidence scores. But in clinical practice, accuracy alone is not sufficient, and we are also interested in metrics like recall, F1 score, or balance accuracy to better understand the model's performance. That is why, in this work, our aim is to estimate the entire confusion matrix from confidence scores, and from there we are going to derive any clinically relevant counting metric. Now, let's look at how we estimate the confusion matrix in more detail. I am going to focus on true positives and false positives here, but an analogous procedure applies for the true negative and false negative entries. Our first method builds on the difference of confidence method, which itself relies on calibration. If the model were perfectly calibrated, each confidence score would reflect the true probability of the sample belonging to the positive class. In that case, the expectation over positive predictions would directly yield the positive predictive value, or PPV, which is the ratio of true positives among all positive predictions. But since models are rarely perfectly calibrated, this estimate is not optimal but will serve as our baseline under the name of confidence-based performance estimation, or CBPE. To correct for this miscalibration, we calculate the true PPV on the validation set, compare it to the mean confidence, and use the difference as an offset. We then apply this offset to the test set mean, giving us an adjusted estimate of PPV on the unlabeled test data. The second method we introduced is an expansion of average threshold confidence, but here I'll refer you to the manuscript for details. Once we have an estimate of PPV on the test set, we multiply it by the number of positive predictions to estimate the true positives. The remaining positive predictions are false positives. We can then analogously use the negative predictions to estimate the negative predictive value to get the true negative and false negatives. And as stated before, now that we have estimates for the full confusion matrix, we can calculate any counting metric we are interested in. We evaluated these two metric estimation methods together with baselines on chest X-ray classification with 3 experiments. First, we looked at shifts in the wild. Here we trained 3 binary resonant 50 models to classify pleural effusion, pneumothorax, or cardiomegaly from chest X-ray images and evaluated performance prediction methods on 2 additional datasets serving as out-of-distribution data. We then permuted the roles of in- and out-of-distribution datasets and repeated the process twice, yielding a total of 18 evaluation points per method. Next, we simulated pure covariate and prevalence shifts by adapting the test sets. For covariate shift, we created 2 subgroups and varied their proportions between training and testing. An artifact was introduced in 80% of sick patients and 20% of healthy patients. The majority group consisted of unaffected healthy patients and sick patients with the artifact, while the minority group was the opposite. Retraining the model caused it to rely heavily on the spurious correlation, yielding higher performance on the majority group but poorer performance on the minority group. In the test set, we then varied the group proportions to simulate covariate shifts. Finally, to isolate prevalence shift, we resampled the test set to achieve a different ratio of sick to healthy patients than in the training set. And for both simulated experiments, we evaluated how the different methods performed across varying shift strengths. The results show 3 metrics: the prevalence-independent balanced accuracy and recall, and the prevalence-dependent F1 score. Calibration error is shown as root-Breer score and adaptive calibration error. Hatched bars indicate out-of-distribution results, solid bars in distribution. ATC and DOC are naive implementations not explicitly designed to estimate metrics beyond accuracy, whereas CBPE and the CM-based estimators compute metrics via the confusion matrix. Overall, our CM-based estimators outperformed others with mean absolute errors around 10 to 20% for the metrics shown here. In the covariate shift experiment, we show the estimated metrics across different fractions of the majority group in the test set. The black line indicates the ground truth. The estimators captured a decline in performance but were overconfident for minority groups and calibration worsened. Here, naive and CM-based approaches performed similarly. On the prevalence shifts, naive methods worked for prevalence-independent metrics but broke down for dependent ones. CM-based estimators captured the trend in F1 but with high error. In short, naive methods ignore prevalence, confusion matrix-based ones capture the trend but lack accuracy, showing that prevalence shifts remain a major failure mode for all estimators. In conclusion, the CM-based estimators bring us closer to practical, label-free monitoring of clinical AI systems, as they allow the estimation of metrics beyond accuracy after deployment. However, to be reliable, they should be paired with an understanding of the deployment context and the shifts that may occur there. Therefore, in future work, we will pair the estimation methods with shift detection, identification, and mitigation techniques.